Today's lesson is about couples. Prior knowledge is you need to know about moments, which we've already studied, and be able to calculate resultant forces, which we have studied. You need to learn what the definition of a couple is. A couple is two equal parallel forces acting in opposite directions and displaced from one another by a perpendicular distance, as in the diagram. What's the properties of a couple? Well, a couple causes a spinning motion, and the other interesting property of a couple is no matter where you take the moment about, then the couple will have the same value. So let's look at taking a moment about A. So I'm going to take a moment about A in the clockwise direction. And if I take the moment about A in the clockwise direction, what does it actually equal? Well, the F here is going through A, so the distance of the force from the position A is a distance of 0. When we take the moments at B, then there's the force F. Here's the force F, and its perpendicular distance from A is D. So therefore we've got plus F times D. So therefore the moment about A is equal to FD. Okay, that's the end of that one. So now we go to diagram 2, and we're going to take the moments about C. And we're going to take moments about C, again, clockwise direction. So we're looking at the force travelling through A, and its perpendicular distance to C is in fact going to be D over 2. So therefore we've got the moment about C in the clockwise direction is going to be F multiplied by D over 2 plus, now looking at the next force, and its perpendicular distance is also from C, is D over 2, half D. So it's going to be plus F on D over 2. So we take out F as a common factor, and we've got D over 2 plus D over 2. So a half D plus a half D is a whole D. So we end up with that being FD. Now, let's pick a point over here, an arbitrary point. Let's call it E. And what we're going to do now is we're going to take moments about E. So we're taking moments about the point E, and we're going to take them in the clockwise direction. So I'm looking at my first force F, and I want to get the line of action of the force. So I track F back. And I need a non-specific distance, so I'm going to choose the distance out from here to be x, which symbolises any distance. So what's the distance of the F here from E? And the perpendicular distance is going to be D plus x. So it's going to be F on D plus x. And it's going in the clockwise direction. If E is the swivel point, then that's going to be going in the clockwise direction. Now, here's the second force, and when I extend its line of action down here, that's the line of action of the force. But you can now see it's going to send it spinning in the anti-clockwise direction. If that's the pivot point and the line of action of the force is this way, it's going to cause it to go in a negative direction. So we're going to end up with a minus f times its perpendicular distance, and its perpendicular distance for me is equal to x. So expanding this out, we've got fd plus fx minus fx. The plus fx and the minus fx cancel, and we end up with a moment fd. So no matter where we take it from, it's always going to have the same moment. Okay, so what we're going to do now is go on to see it being used in a practical problem. Okay then, next page. So what we're going to be doing here, and what you're going to be doing for the exercise, is we're going to actually simplify the system that they've given us in diagram number 1, which I've just put a dot in the middle of, and we're going to create a brand new diagram with just one single force and a certain distance. So the first thing we've got to do is we've got to work out the magnitude of our resultant force. So let's use the normal I and J direction notation. So I'm going to look at the magnitude of my force. Before I can work out the magnitude of the resultant force, I need to work out what the actual force is. So I'm going to go systematically starting at AB, and then I'm going to go to starting at AB, and then I'm going to go to BC, and then CD, and so on and so on. So therefore, if I'm looking at AB, I've got 1 going to the right, so that's going to be 1I. And then next one, this one is going down, so it's going to be minus 1J. And then this one here is going to the right, so it's plus 2I. And this one is going down, so it's going to be minus 3J. Very simple. So F is equal to 1I plus 2I is going to be 3I. Minus 4J. Now the question actually did specify working out the magnitude of this force. So the magnitude of this force is going to be the magnitude of 3I minus 4J. It's a 3, 4, 5 triangle. So therefore the magnitude is equal to 5 newtons. And that's the end of part 1. Now, what it's actually asking you for in the question is to find the distance of the line of action of this force from A. So we're going to assume that the force is up above A, and we know that the force is 3 along and 4 down. So I'm just drawing a sketch here, 3 along and then 4 down. So therefore we know that the resultant is as on the diagram, with the resultant 5. So I'm going to represent that on my diagram up here. Please use a ruler when you're doing it, and copy this example out neatly. As with the previous page, copy out the page very neatly. So they've asked us find the distance of the line of action of this force from A. Now the definition of distance in mathematics is always perpendicular distance. So what we want is the perpendicular distance from A. Now we know that these two systems have to be equivalent. By equivalence we mean they have to behave in the same way. I've got the correct force, so I know that the force in the equivalent system is definitely 5, and according to this diagram down here, it's going off to the right and down. That's represented on the diagram. What I've got to do now is calculate the specific distance in order to get the same moment, the same spinning action. So what I'm going to do, since they asked me to focus on A, is I'm going to take moments about A. So I'm taking moments about A, and from my equivalent force diagram, which is this diagram here, my equivalent force diagram, clearly the moment's going to be in a clockwise direction, and it's going to be 5 times its perpendicular distance, which is going to be d. So I know it's going to be 5d. And I know it's going to be equivalent to the same moment on this one. So now I'm going to have to work out the moment for this system here. Well, the first force I'm looking at is the force of 3 newtons going down. But because it passes through A, because this force passes through A, I know this 3 Newton force hasn't got any distance from A, so the moment's going to be 3 times 0. I'm now going to go on to this force here, and its line of action goes through A. And because the line of action goes through A, it doesn't have any perpendicular distance, so therefore it's going to be 1 on 0. Now I'm looking at this force here, and the direction of this force is downwards, which means it gives me a clockwise spinning motion, which is in the same direction as my A. So I've now got the force was equal to, can't read it, I rubbed it out, shocking. Oh, it's equal to 1. So it's going to be plus 1, and the perpendicular distance, well, we need to read the question. Each side of this square has got a length of 1 meter. So its perpendicular distance from the center of rotation is going to be 1 meter. So it's going to be 1 on 1. And then we've got one more force left, which is the 2 Newton force, which is going this way. And again, we're looking at the force. We're looking at its perpendicular distance. Perpendicular distance is going to be 1 meter. So therefore, is it clockwise? Yes, it is. We can see it is spinning it this way round with respect to A. So it's going to be a plus 2 times 1. So when we work out the total moment on this side, we've got 3 lots of 0 is 0, 1 lot of 0 is 0, 1 lot of 1 is 1, plus 2 lots of 1 is 2, which gives us 3. So we've now got 5d is equal to 3, and we were asked to calculate d, which is going to be 3 over 5. It's going to be 3 over 5 meters. Okay, that's simple enough. That's the end of part 2. Now, I just want to give you a chance just to take that on board, because what we're going to do now is we're going to go right back to the beginning in order to answer the ratio in which the line divides line AB. It's very important you pay attention to this and study it, and then you'll be able to do the examples. So I'm going to reset the page. I'm going to remind us what we've already actually achieved, and what we've already achieved is that we know that F, the magnitude of F, was equal to 5. We know that the magnitude of F is 5, and it's on this diagram. And the ratio in which this line of action of the force divides the line segment AB. So I'm now going to, when it says line of action, it means extend this line on, straight line, and where it cuts. And I don't know where it cuts, so therefore I'm going to call that a distance x. Now, since the whole length is equal to 1, then the length over here on this side must be 1 minus x. I'm going to call this point E. And I'm going to represent this point E on this diagram as well. So it's going to be x, and that's going to be 1 minus x. Now, in order to work out the ratio that divides the line A and B, what is that ratio? Well, the ratio is already there. Let's pick up some easy marks. What is the ratio that it divides the line in? It divides the line in the ratio x to 1 minus x. So that's what I need to find x. Once I found x, I sub it back into that formula to get the ratio of the 2 lengths. Okay, So, how am I going to do this? Well, this time, this is a trick question. When they ask you for something like this, you see where it cuts the line in question, and that's where you take moments about. So we're going to take moments about E. And again, I'm going to choose to take moments in the positive direction. So working off this diagram here, let's look at the force along AB. Because AB passes through the centre point, it means its line of action has a distance 0 from E. So therefore I've got 1 on a distance 0. So that's the AB taken care of. Now I'm going to take a moment for BC. And BC, what's the perpendicular distance of BC from E? Well, I can quite clearly see it's 1 minus x. Now, this arrow is going down, so it's going to have a turning effect this way, because this is the pivot point. So it's going to pivot it in a clockwise direction, hence it's going to be plus. So what was the force? The force was 1. What's its perpendicular distance from E? It's 1 minus x. Okay, so we've done the 1 Newton force. Now we're going to work on the 2 Newton force. And there's the line of action of the 2 Newton force. So what's its perpendicular distance? Well, its perpendicular distance from E is this distance down here. And again, if you read the question, what's the length of a side? It's 1 metre. So this force, 2 newtons, has a perpendicular distance of 1 metre. Does it have a positive turning effect? Well, this is the pivot point. The force is pulling it this way, so it has a turning effect clockwise. So yes, that's a positive. So it's going to be 2 on its perpendicular distance, which is equal to 1. Okay, so that's the end of DC. I'll give you a few minutes to study it because I'm about to rub that out, because all it's going to do is make everything else a little bit unclear. And now what we have here is we are going to take moments dA for the force dA. So we're taking moments about dA, and it's going this way. Its perpendicular distance is x. Now, as you can see, because it's coming down here, it's going to have a turning effect which is going to go against this arrow, and therefore it's going to be a negative. So it's going to be a negative. What's the value of this force? It's going to be a value of 3, and it's going to be 3x, because its perpendicular distance from E is going to be x. And now we're going to compare it to the equivalent force system, which remember is this one here. And the equivalent force system, our force is going through E. And because it's going through E, our force is 5, its distance from E is 0. That's how this trick works. So now we're going to work this out. That's 0. That's going to be 1 minus x plus 2 minus 3x is equal to 0. Minus x minus 3x is minus 4x plus 3 is equal to 0. So we've got minus 4x is equal to minus 3. Change the signs. X is equal to 3 over 4. So we go back to what we were trying to do at the beginning, which was our ratio. And our ratio is x on 1 minus x. So it's going to be 3/4 on 1 minus 3/4. So it's going to be 3/4 on 1/4. And then we're going to, because it's a ratio, we can multiply to get rid of the bottom of the fraction. So the ratio will be 3 to 1. That's the end of example 8.8. Right, going on to the last example. If you give you a chance to read it. While I just prepare the question. Okay, you've got your sides are length 1, so same as before. Be careful, if they're rectangles, there'll be different sides. So we know the sides are all length 1. So I'm going to indicate that in blue so we don't confuse it with a force. And I'm also going to put it in a circle. So again, we don't confuse it. So the blues are in actual fact the distances. So looking at the forces, I'll do in black. So the 6 Newton force is going that way, and its value is 6. The 4 Newton force is going that way, value 4. The 2 Newton force is going up, value 2. And the 1 Newton force is going that way, value 1. Now the other interesting thing about this, and you need to be very careful with this, there is a couple. And the couple has a moment value of 4 Newton meters in the anti-clockwise direction. So therefore, I am now going to put the couple in red, and I'm going to write it using moment notation. So basically what I'm saying is there's no overall force up and down. There is just a moment of value 4 Newton meters in the anti-clockwise direction. Don't forget, when you do the resultant for a moment, because the two forces are equal and opposite, they cancel each other out. And that's why you don't need to know where the couple is on the diagram, because when you're working out the resultant forces, it's going to cancel out anyway. So we are now going to work out the force. So we'll just start off in this corner and move in a anti-clockwise direction around. So the first one is 1 in the I direction, so it's equal to 1I. This one is going up, so it's plus 2j. This is going to the left, so it's minus 4i. And this one is going down, so therefore it's minus 6j. Then we do a tidy up line, and we've got 1i minus 4i is minus 3i. 2 minus 6 is minus 4j. Oh, they're being nice to us, choosing Pythagorean triples all the time. So the magnitude of our force it's a 3, 4, 5 triangle, so it's equal to 5 newtons. Which direction is it going in? Well, it's going, let's make that the starting point. So it's going 3 to the left, and it's going 4 down. So it's 3 to the left, 4 down, which gives us a resultant force which is going in that direction. Okay, so we have found the resultant. Now they're asking us to find the distance of its line of action from P. Find the distance of its line of action from P. Now this is where the equivalent forced diagram comes in. Now the big question here is, where is this force? That's the big question. And in the end, it actually really doesn't matter. So here is my force. I just draw it there for the moment, just to keep life simple. Just put the resultant on it. And pull that off to one side and seal it together. So where is it? Is it below P or is it above P? Now the interesting thing is, just for future reference, it doesn't matter where I put it. If I put it in the wrong place, the distance comes out as negative, and therefore you have to write a written explanation saying, oh, D came out as negative, which meant my line of action, let's say it was below P. My line of action isn't below P, it's parallel and above P. So I have absolutely no idea where this force is. It could be over here, it could be over there, no idea. So what I'm going to do now is I'm going to throw the force up there. Now I'm going to take moments about P. And because I'm taking moments about P, I need the perpendicular distance from P to the line of action of this force. So what I'm going to do now is right, use a dotted line. And what I'm going to do is, once again, I'm going to try and mimic roughly that line, which I hopefully have successfully done. And then if I've done it properly, then I just join it on the end of this one. So now I've got the line of action, the continuance. And now I need to put on the perpendicular distance. So drawing the perpendicular distance in. Again, I'm going to use dotted line, purple, and the perpendicular distance. Now, here's my line from P, and what you've got to remember is, when you're taking moments, it can't be at an angle. It has to be a perfect perpendicular distance. So I'm doing that by eye. I hope that is roughly right. When you're using your ruler, just make sure that you've got a proper right angle in there. And we're going to call that distance D, and that's what we're trying to calculate. And we know that the equivalent force system has a force of 5. Now, this is our equivalent force system. So clearly what I'm going to be doing is I'm going to be taking moments about P. So I'm going to be taking moments about P, and it's fairly obvious that this is going to give me a turning effect which is anti-clockwise. Now you could argue, why did I choose that? If I'd chosen this arrow here to, instead of being here, actually being below, down here somewhere, then what would have happened? Well, it would have been going the other way. It would have been a positive. Doesn't really matter. So now, so that's in the positive direction. So, whoops, I didn't mean to do that. Put that back. So we've got to have 5D. So it's going to be 5 lots of D is equal to. So we're now taking moments about P for these forces. Well, for that one, it's just going to be 1 times 0. And for this one, because it goes through P, it's going to be 6 times 0. Now, for the 2, it has a perpendicular distance of 1. It is also spinning in the same direction as my defined arrows, which I've now defined as being my positive direction for this problem. So it's going to be 2 lots of the perpendicular distance, which is 1. So it's plus 2 lots of 1. And now I'm on to my last force, which is 4. And again, it's going to have, if P is pinned, it's going to have a turning effect going this way. And it's going to have a distance of 1 from P, a perpendicular distance of 1 from P. So it's going to be plus 4 times its perpendicularness of 1. Now, what people then forget, quite sadly, is that there is a couple, and the couple has a moment. And this is where it is here. It's 4. Is it with my arrows? Yes, it is. So this is what people forget. When you get these problems wrong, you've forgotten to add in the 4 Newton meters that was given in the question as a couple. So you need to watch out for that. That's the most common mistake. So if you've mucked up a question, go back and check that. Now, looking for our D, 5D is equal to 0 plus 0 plus 2 plus 4 plus 4. 4, 8, 10. So I've got 5D is equal to 10. So D is equal to 2 meters. And that's the end of it. Please note, at the top of each page, next to each example, is the questions that I've set. So for this example, I'm setting 4, 5, and 6. And for the previous example, I set numbers 1 and 3. So the work is set within the activity.